if you now say that this slide is Euclidean, right? So it's a Euclidean plane, then the blue line would be a geodesic and the yellow ones will be not, right? So because they're longer. They all go from point A to point B, but only one of them is geodesic. And then for Riemannian manifolds, we have on top a Riemannian metric, which I call now Gij. So Ij are just the indices of the tensor, right? So Noemi has shown it as matrix form, but I introduce it here now as a tensor. So it's written in indices, right? So the Riemannian metric is a second order tensor. So it takes two vectors and produces a scalar, okay? And then the condition for geodesics is that they extremize arc length. So when you look at this arc length integral there, it's also taking, like we've seen before, the square root of like the inner product between the velocity vectors, right? And I've written it out here in indices. So also everywhere on the slides, I use Einstein notation. So this equation in the square root is actually summing over all i's and j's, right? So this is a scalar quantity in the square root. Okay, and so this integral there integrates over all the path. So S is the parameter, right, as we've seen before as well. And now when you try this length integral for every possible path between A and B, the one that minimizes L is the geodesic. Okay, and we've also seen that they satisfy the geodesic equation, which is there on the bottom. So it's the second derivative of gamma with respect to the arc, or with respect to the parameter S. And then we have here the Christoffel symbols and the two velocities. Okay, and now I have written this equation for one component of gamma, right? So in two-dimensional space, I would have two gamma components here, right? So I have one equation for gamma 1 and one equation for gamma 2. And for n-dimensional spaces, this will be n equations like this. And again, here on the second part, there's Einstein notation. So I would sum over all B's and C's. Okay. And then another recap to Christoffel symbols. So here's again the equation. I think I've written it a bit differently than you in the beginning. So it's again Einstein summation. So this I index here appears here on the top and here on the bottom. So we sum over the i's. And here we can see in the output that the Christoffel symbols have three indices. So they behave like a third order tensor. Actually, they're not a tensor, I think, but I mean, they behave a bit like it, and they have three indices. And then also, again, here in the geodesic equation, we'd see it again that here we have the Einstein notation. Okay, and also here I have written the indices on the top, right? So usually they're written on the bottom. So here I've introduced Gij with indices on the bottom. And when you write them on the top, this means that you invert the matrix. Right? So this would be the inverse of G, like in a matrix form. Right? So if we would now multiply Gij and this one here, then we will get the Kronecker delta. Okay, so the identity matrix in index notation. Okay, and then what we also see is for constant metric, all the Christoffel symbols are 0, because the Christoffel symbols only depend on derivatives of the metric, right? And whenever this is constant, there is no derivative, right? It will be always 0. And this means already that geodesics are straight for constant metrics. It doesn't even need to be Euclidean, but if it's like a constant matrix, they will also be straight. Okay. Anything more here? Yeah, so in this equation, you can see that when all these symbols here are 0, then it just says that the second derivative is 0, right? And this means that the curve is straight. Okay, then it was already written on the slides that geodesics extremize the arc length functional. So it's not necessarily a minimum, right? It can also be like a saddle or so of this L function. So for the curve here means, for the sphere, it means that the red thing here is a geodesic, but also the other one going the other way around. Like the other part of this great circle is also geodesic. And you can see it because it also satisfies the geodesic equation, right? So the geodesic equation is, I mean, you can see it looks like a ordinary differential equation. I mean, it's second order, but still when you select an initial gamma and an initial velocity, you can shoot geodesics into certain directions. And here, if you shoot from P in Q direction, you get the red segment. And if you shoot in the other direction, you also reach Q, but the other way around, right? But still it's a geodesic because it satisfies the geodesic equation. And it also has the property that L becomes stationary for the other geodesic. Okay, then we have seen this image before. So this shows that basically strings naturally find geodesics. Okay, so when you put this the string here on the fruit, it will always be a geodesic automatically. I mean, the fruit has to be convex so that it works in real world, right? Because the string has to be constrained to the surface. And this doesn't work anymore in real life when it's non-convex. But so this means that all the forces that are left, so if you imagine that here's some tension on this string, right? So that you pull a bit, then all the forces anywhere on the string will be along the string and there will no normal component, right? And the idea now is to use this insight that strings naturally find geodesics to find geodesics, right? So because the problem is that the geodesic equation here is again some kind of shooting problem. So you can select one point in one direction and then you can shoot into different directions and you see where you get. But when we want to find something like a geodesic going from this toothpick to this toothpick, this is not so easy, right? Because we can only shoot and we have to find some initial directions such that we read there, that we reach the other point. Okay, here's another example on different spaces. So whenever we get these like the property that it doesn't move anymore, we found a geodesic, right? And it's important to imagine that the string here on the surface is without any stiction, right? So it means that whenever there is a normal force, that it will also be relaxed, the normal force, after some time if we wait long enough. And yeah, for closed strings, this also works. So we can use this idea to also find closed geodesics, right? So not between 2 points, but which like encircle this thing completely. Like also on the sphere, like each great circle is a closed geodesic, right? So you will come back to the same point after one cycle. And the same is true for these examples here. So here's one on the torus and here's another one. And this is this weird shape, right? Okay, and now because we will need this later, I want to find an algorithm that basically simulates these rubber strings on surfaces, and then we can use this to do mechanics. We will see later why. Okay, so the idea is to now find another curve which also has a time parameter, so not only arc length. And the idea is that we can start with an initial curve like each of the yellow ones, and then we let time pass and all of them will converge to geodesics. So this is the idea. Okay, we want to derive some dynamics for this change in the curve such that it converges to geodesics. And this is what we do. So it's just again the geodesic equation, but now we don't set it to 0, but we say that the change in the curve, so this is with respect to time, this is with respect to space, right? That the change in the curve is equal to the geodesic equation. And it's maybe not that clear, but if you simulate this, you see that this will converge to a geodesic if you find with some string, if you start with some string between 2 points. Okay. So still it's the problem. I mean, this is now a partial differential equation. It's quite complex and it's continuous. And the first idea now is to discretize this in time and space. Okay. And my discretization of the rubber string here, so this would be the continuous one as PDE, is to write it as an ODE by breaking it down into small spring elements, right? And each of the spring element would like to have 0 length, right? So then it would be happy if it's exactly at 0, right? So, I mean, this one here has a resting length. I would like one without, okay? Okay, so as I've said, I would like to discretize the string in time and space. So before we had gamma of S and T, and now I introduce some space step delta S and some time step delta T, and I call it gamma again, but now time is here an index parameter, and K is basically the index of the point on the string. Okay. And now the idea is to discretize this continuous PDE here to write it in this discrete points. Okay. So again, this is the PDE. This is what we want to discretize. And this is what we get. Looks a bit complicated, but actually it's not that complicated. I will just talk about the components like component wisely. So this one here is just the discretization of the second derivative in space. Okay. This one here is the first derivative in space, but using central differences, right? So it's not a forward difference, it's a central difference. And for the derivative in time, I have also used like this difference quotient, but as forward derivative. So it's not central. And I've replaced it to see the new update here on the left-hand side, right? So if you can see that here I have gamma t plus 1, here's gamma t, and here's divided by delta t, and I rearranged it to see how to update gamma. Okay. And then by just computing this, we can update gamma. Okay. And this will move the points around on the string, and like for Euclidean spaces, when you would do this once, you would get this. Like they will move closer to a straight line. Okay, then the last point to talk about is the boundary conditions for this. And there are two options. If we want to find geodesics between 2 points, we would just set the initial and the final point to the 2 points we want. Okay, so this is quite simple. And if we want to find closed ones, we just connect the last point back to the first. Okay. So also this is simple, but I mean, it has to be taken into account in the equations here, right? So you have to take care that like index 0 is fixed, for instance, or that index 0 is index K. So if you have the closed string. Okay. So then I have one example here, which is the first boring example. I've fixed this red string here. So this is the discrete string. The blue points are the points on the string in Euclidean space. And then I let it converge and I get the green one after convergence. So this found a geodesic between A and B. Okay. I mean, in Euclidean space, it's quite boring. So I would like to show one more example. And this example is using the so-called azimuthal projection of the sphere. So it's a kind of mapping the sphere to a disk. And it works by not changing the longitude at all. Okay, so we use as the angle here the longitude of each point. And for the radius here, we just use the latitude, but we offset it by 90 degrees and invert it. Okay, so the center would be the North Pole. So this would be 0, and then we go to 90 and to 180. Okay, and then we would get this map of the sphere here. And then you can express it also now in polar coordinates. So this would get us from here to here. Okay, so if the sphere would be a unit disk, then we can take this space here, parameterized by r and theta, and then by going through all the points, we would get the points on the sphere here. Okay. And now if we say that we have the Euclidean metric on the sphere, we can use this law to pull the Euclidean metric back to this disk. And then the metrics look like this. Okay, so this is usually like one standard way of getting Riemannian metrics by pulling back Euclidean metrics from somewhere else to a space that's easier to handle, right? And this is what's happening here. Okay, so we would like to find Euclidean geodesics, for instance, on the sphere, but compute them here in this disk domain. Okay, and here are some examples of these. So let's first look at the pink one here. So I started with the pink one and it converged immediately. So this was already a geodesic, which makes sense because it's a longitude, right? So it's part of a great circle, so it's geodesic already. Then, oops. Here's again, so each time the dashed lines are the initial string that I just said. I mean, these are parts of the circle, and the solid bold lines are the ones it converged to. Okay, and yeah, you see like that for this one here, it moves towards the North Pole, and here it moves towards the South Pole, right? And when you look here in the sphere representation, it becomes pretty clear that they become shorter on the ball. Okay. Good. This was the starter. I showed the algorithm that I used to find geodesics. Okay. And I mean, I use it for these settings where I know the two endpoints, or I know the topology that I want from the string. For the geodesic equation, I mean, we can use this one to shoot into directions. But if we want to find geodesics between 2 points, then it's better like this, right? So because we can fix it between the 2 points we like. Okay, but now let's go into mechanics. And the next 3 slides are maybe a bit equation heavy, so I apologize for that. I like to start with a reminder on Lagrangian mechanics. So we've seen it also before in the talk by Nathan. So we usually define something called Lagrangian, which is the difference of kinetic and potential energy. So T is here kinetic, U is potential. And then we have something called the action integral, or it's actually called the Hamiltonian action integral. Even, I mean, it doesn't involve in Hamiltonian, but it's still called Hamiltonian action integral. And this is integrating L from some time t0 to some time t1 over some given trajectory. Okay, so suppose somebody gives you a trajectory, q of t and q dot of t, then you can compute the action by evaluating this integral. And if this action is stationary for some trajectory you get, then you know that this is a true trajectory of the system. Okay, so this is what's called the principle of least action. Okay, I mean, this, it looks first quite complicated because you would need to look over all possible trajectories, right? So this is hard to do in practice. So what usually happens is that you then write the Euler-Lagrange equation again, and then you get this well-known form of the dynamics, right? So it now was again transformed into an ordinary differential equation and initial value problem, right? So if you know some point and some velocity, you can integrate the system to get trajectories, right? But if we want to find trajectories between 2 points, this is not easy. Okay. So, and I would like to look a bit more into the geometry of this action integral. Okay, so here's again a summary on what's going on here. So this integral here allows us to judge if a given trajectory of a mechanical system is a true trajectory, like some that the system would do, right? But what we would need to do to compute this is somehow evaluate this for all possible paths and check that the one we have makes this integral stationary. And this is hard. Okay. But we can use the same idea as for geodesics. And then we get ordinary differential equations as initial value problems, and then solve those ones, right? So this is the same as for geodesics. There we had the arc length integral, and we had the geodesic equations. And here in mechanics, we have the action integral and the Euler-Lagrange equations, right? So it's just the same thing. Okay, then there's an alternative version of the principle of least action. It's called a Maupertuis principle of least action. And the difference here is that we don't integrate over time, but over space. Okay, so here in this one, we had time in the integral. So we needed to find some way or somehow trajectories that go between 2 points, but also at the same time. Right, so the t's are fixed. Okay, and in this formulation here, we only need to integrate over space. Okay, and here in this equation, p is the momentum, which is dl by dq dot. Okay, and dq is now the integrand. So, but important to note is that this only works if we select an energy on top. Right, so if we select an energy beforehand, we can always reconstruct velocity from a configuration path. Okay, so if you know some path in configuration space and you know the energy of the system, then you can compute the velocity. Right, so it's basically redundant information. So in Lagrangian mechanics, we remember for each point the position and the velocity. And in this form, we remember just the total energy and the configuration path. But this is the same information. Okay. And yeah, this brings us now to just configuration space paths. Okay, so before we were in state space, so in 2 n dimensions, we had one trajectory for q and one for q dot. But now we're just in n-dimensional space, right? Because we don't need to take care about velocities anymore. Okay, yeah, and as I said, we can always construct them, reconstruct them when we just take the constant energy. I think the presenter broke. Can you switch maybe to the next slide? Okay, thank you. So this was shown before. So when we have energy, we can remove time from the equations. And this is what I've done here on the top. So the first integral is again the Maupertuis principle of least action. And now I've rewritten it in terms of kinetic energy. So momentum times velocity is kinetic energy, right? So I've replaced it here by 2t, okay? But then this brings us back to a time integral, okay? But we don't want time. So let's get rid of it again. So and in the next equation, so I start again with what's now in the integral, right? So with 2t, 2 times the kinetic energy. And 2 times the kinetic energy is just the inner product of the mass tensor and the velocities. Okay. And here the dots above the q mean it's q differentiated by time. Okay. So q dot are now physical velocities. Okay. So this is 2 times the kinetic energy. And what we can do now is replace the physical time by a fake time. So we now don't use physical time anymore, but we use the arc length parameter, which we now call S. Okay, So this primes at the Q mean it's not differentiated by T, but by S. Okay, and when we do this, we also need to introduce 2 times ds by dt because we have 2 times Q, right? So this way it's squared there. Okay, and then on the right-hand side, I've just written another form of the left-hand side. So kinetic energy is total energy minus potential energy, right? Because there is no other energies. Okay, and then when I rearrange this equation, I get the one on the bottom. So this tells us how to relate physical time to arc length. Okay. Thank you. Okay, so last equation slide. Just a hint again, geodesics look like this. Okay, and now I would like to rewrite this action integral such that it looks like this. Okay, so I again take this one here. So this was the final step here. I take the integral over 2 times the kinetic energy. And now I replace this dt by ds. Okay, so I replace physical time by arc length. And then I get this. Okay. So now you see also here I've on the integral s and not t. Okay, and then when we rearrange this equation here, it becomes this. And what you can see that this term here with the blue underline acts like a metric, right? So when you compare it to the geodesic equation on the top, yeah, it behaves the same way. Like we have the q primes there, and this this form on the bottom, which I now call J, Gij. Okay, and I call it J because it's called the Jacobi metric. So this term in the box is called Jacobi metrics. And so this is the natural metrics for mechanical systems with potential forces. Okay, so Nathan mentioned for systems without gravity, it's the inertia matrix. And now if we also have potential forces, it's this Jacobi metric. And what you can also see is that when you say that we don't have u, so u of q is always 0. So it's again then a system without potential. Then this is just again a scalar times the inertia matrix, right? But a scalar doesn't change the geodesics. Okay, so this generalizes also to systems without potential. Again, please. Okay, so I mean, I think this is the most important statement of my talk. So we can find trajectories of mechanical systems by just looking at geodesics of the Riemannian manifold. And the Riemannian manifold is the configuration space endowed with the Jacobi metric. Okay, and then if you find geodesics in the space, these will be trajectories of the mechanical system. Okay. Please. So now I have 2 examples how to use it. And one is, yeah, the same question as before. How can I find trajectories between 2 points? So let's say we want to go from QA to QB with a natural trajectory, so no control and so it's just about the pure dynamics of the system. And can you go once more? So when we have Lagrangian mechanics, the principle would be shooting. So we would go to QA and select random, or maybe not random, but more systematic initial velocities and simulate the system and hope that we at some point hit QB, right? I mean, we could also maybe have some gradients and so on, or estimate gradients, but this is the rough idea, right? So for the initial value problems, there's no way of constraining the space to all the paths which actually hit QB, okay? So now what we do in the geometric version is to just take a string again, attach it to the 2 points QA and QB, and let it converge to a geodesic. Okay. So again, we now use the Jacobi metric as Riemannian metrics, and we just let it converge. Can you go to the next? Okay, and this is what I got for this. I mean, there are many things here on the slide. So first, on the left, on the top, I have the configuration space of the robot. So again, the blue one is the one I started with. So I just started with a Euclidean string. I mean, it's Euclideanly straight string between the two endpoints. And then I let this algorithm run, and it converged to the green one. So you may notice that now the green one has a bit more points than the blue one. So I added some more features to resample it a bit from time to time to get the resolution better. Okay. Yeah, just a side mark. Oh, can you go back? So now what I try to validate this is to now actually simulate the system with the Euler-Lagrange equation. So I take the Lagrange equation and use ODE 45 to simulate the system. And I've chosen the bottom part here. So this is the initial condition, and I reconstruct the initial velocity by knowing the tangent there and the total energy, right? And then when I simulate the system, I get what's shown there on the right, and you see that it hits the spot, right? But it doesn't do it with zero velocity, okay? Because I need to select the total energy beforehand, right? And if I would select another total energy, also the green string will look different because the matrix is different, okay? So this is the big difference between systems in potential fields and systems without potential field, right? So there the green string would always be the same, like no matter what the energy is. Okay, now I'm ready. Okay, the second example how to use it is periodic orbits. So before we fixed two endpoints, and now the idea is to find periodic orbits, like that after some period time t, you get back to the exact same state. So, and then it would continue forever like this, okay? But how would you even do this in Lagrangian mechanics? Because all we have is this condition that we want the configuration to be the same at 0 and at t, and that the velocities are the same at 0 at t and t. But we don't know the states here, like we don't know where to start and with which velocities. And we also don't know the period time. So, I mean, we could do a lot of random search or so, but I mean, there's no systematic way how to find this. But with this string idea, there is. So we just create a string of the correct topology and let it converge. Okay. So here's this idea again, and now I think Noemi mentioned it, that it's always like toroidal spaces for mechanical systems or for systems with joints, right? So we have the double pendulum. So it's a system with two joints, and we can represent it as a torus, right? And on the torus, we can create many different kinds of closed strings, right? So we have a string that goes once around the one hole or around the other hole, or once about both holes, and so on. And these are the ones how they would look like in Euclidean space. So if the metric on top of the torus is Euclidean, you will get these blue ones. But I would like to see how they look like when you take the Jacobi metric, right? So then we find velocities of mechanical systems. And the idea is now to start with like Euclidean geodesics on Tori and let them converge to geodesics for the Jacobi metric. And here's one of those. So this is an animation how the rubber string converges. It's now here displayed like not on the torus because it was complicated to animate there, but I mean you have here the two axes on the torus, right? And here is the rep at pi, right? So here it flips from pi to minus pi, right? And you can see in the end, in the beginning it was a straight line, but then after some iterations it becomes this weird shape. Okay. So the blue one is the one I started with, and the orange one is the final result. Okay, and we can also simulate this. So this is how the orbit looks like. Again, it's without any control. So it's just selecting any point on the string here and computing the velocity and then just let it run. And then in the simulation, we see that it is indeed a closed orbit, right? So it comes back to the initial state after some time. And here are some more of these. Also, I mean, 4 of these now on the torus. And we can see that they all bend a lot, actually. And in the animations, you can see like what you can get. So these are all periodic orbits of the double pendulum. And importantly, these orbits are all orbits which turn one of the joints at least in full cycles, right? Because we enclose holes of the torus. Okay, I'm skipping this. I just wanted to mention one last thing, and this is that we can also find periodic orbits that do not turn one of the joints in full cycles. And I think these are actually the ones which are most promising for robotics, because usually we can't turn joints in full cycles, right? And we also find those, but it's a bit more complicated, because there you don't have the property that that the topology of the space prevents them from collapsing to a point, right? So if you would like to find a geodesic on a sphere algorithmically, like once you have a small error, it will collapse to a point, right? Because all the springs want to go to 0. So there needs to be some care on top that this doesn't happen. But we find them as well. Okay. So here are some examples of these closed geodesics again for the double pendulum, but now they don't encircle full holes of the torus. Okay, and yeah, I think I'm also skipping this. So what I tried here is to embed the space that we get from the Riemannian metric into some higher space. So we have seen that we could embed the sphere here. So we could embed the sphere into the disk, right? And there we could, there we got a new metric here by pulling back the Euclidean metric here. But now for our mechanical system, we just have this side. And I wanted to try the opposite direction. So to find some space where the pulled back Euclidean metric is the one we see on our mechanical system. And I mean, this is quite preliminary. I did it last week, but this is what you get. And you can see that indeed this H shape is a geodesic of it. Okay, then that's it. Yes, please.
Thanks for the nice talk.
Could you go to the microphone?
Thanks for the nice talk. In the last example you showed for the torus of their optimization, it depends, of course. I mean, if you evolve along the topology, it will depend not only where you start, but also on the homology class you choose, for example. So it only finds the one that actually matches that starting condition, right?
Yes.
Okay.
So, I mean, also for one homology class, I think there are multiple. I mean, for each energy,
multiple because if you want more rounding.
Yeah. So, I mean, so one way is to change like the roundings, right? So to go to different homology classes, but also within one class, it's multiple geodesics.
Yeah.
So, I mean, we have the topology of the string as one parameter, but also the energy, right? And for other energies, we also get other geodesics in the end.
Okay, thank you.
So the question I had was, so you were discretizing this partial differential equation you've constructed to converge to these. Have you considered taking the finite element approach, sort of stealing from more mechanical engineering type fields?
Considered but not done. So, but what I've implemented is an implicit solver for it. So I think this is very important when you do it in practice, because I mean, with this explicit one, I mean, I think it works well as illustration example, but I mean, for this kind of relaxation dynamics, explicit doesn't work well. So you need to choose very small time steps. And I mean, we're not interested in exactly knowing the convergence, like at which time we're at which string, but we just want to know where it converges. And there are implicit solvers with a large time step work best so far.
That makes sense. Thank you.
Hi, great talk. I just wanted to ask if you considered adding end effector constraints as well. For example, if you have a manipulator that wants to clean a table periodically and you constrain it to a plane, is there a way to encode such constraints with your method?
Probably. So I think you could maybe write the equations of motion in a way that they're constrained. I mean, then it works out of the box.
Uh-huh.
If there are constraints on top, I think, I don't really know.
Okay, cool.
I have a quick question. Correct me if I'm wrong. The example you showed us doesn't include any control input. No.
No, it was all without control, just the intrinsic dynamics.
Okay. If we add a control input, if we want to do some active control, then how the formulation is going to be changed?
Okay, so I think the bad news is that it doesn't really work because the system is no longer conservative, right? So all this formulation works for conservative systems, like anything that we can write in this m of q times plus c of q plus g of q equation. Also, when there's damping, it doesn't work, right?
Okay.
So our approach so far is when we did this kind of things on actual systems is to compensate for damping with controllers and stabilize the periodic orbits of the system, right? But the modeling is always for the conservative system and also the analysis.
I see. Thank you.